Okay, so I'm Sarah, and just to talk a little bit about me, since I don't really know anyone here at this conference, clearly, if you can tell by my accent, I'm not actually from the UK. I live in the United States. It's called Wichita, Kansas, in case none of you have ever heard of that, but it's quite literally like the center of the entire United States. Some people call it the flyover states because there's not actually anything to do there. You just fly over them. But that's where I live, and my background is a little less actually in cybersecurity and more on the statistics, data science, computer science side of things. So this talk today, which we'll get into, is probably one of the least technical talks that you'll hear today, but I want to encourage you to think that that's not actually a bad thing and that it can still be interesting and applicable to cybersecurity. But yeah, so I grew up in Michigan. I come over here quite a bit for work, though. We've got offices in Manchester and stuff. I had meetings here this week, so it kind of worked out. But in general, like I said, don't necessarily consider myself the most, technical cybersecurity resource, but much more of a statistician and math person. And so this talk came about because I was listening to some dumb reality podcast about dating and relationships, and that's just how I spend my time, and it is what it is. But there was a certain episode they had a guest speaker who was a behavioral scientist, and she was actually like a relationship scientist, which I didn't know was a thing, but spent her career studying the behavior behind relationships and things like that. And she started talking about just humans, who we are, why we make the decisions we make, and why people tend to act against their own best interest, which was a really fascinating concept to me. And she started talking about this computer science algorithm, and immediately I was like, oh, okay, now this is really getting interesting, and was applying it to dating and relationships. I was like, that's such an interesting concept. And she referenced this book called Algorithms to Live By. If you haven't read it, I'll highly recommend it. It's what some of this talk is going to be based on, but it's called The Computer Science of Human Decisions, but it's basically this book that takes computer science algorithms and applies it to daily life and how you can optimize your life with computer science. And that is just right up my alley because I really like to understand psychology and why people make choices. I really like math. I really like computer science. So I immediately knew I needed to read this book, and that's kind of how this whole talk was born. And then I started reading this book and I thought, we can apply this to cybersecurity too, right? Because algorithms at a high level are really just concepts and constructs of how to do things. And so we could apply this to computer science. So for the rest of this talk, what I'm going to do, I'm going to go over 3 different algorithms. I'll give you the computer science use for an algorithm, an example of how to apply it to life, but then also an example of how you can apply it to your job, cybersecurity, running a cybersecurity department, or the things you're doing in daily life. So, before we kick into some of the algorithms, though, I just wanted to show my favorite quote from the entire book. You don't need a therapist, you need an algorithm, which I thought was hilarious. I've adopted that into my daily life now, so that is officially my new quote. But I think it's really interesting because it talks all about, how you can actually use algorithms to make better choices instead of therapy, although I still highly recommend therapy. But let's get into the first algorithm. And so algorithm 1 is called the optimal stopping algorithm. And it actually all stems from a really famous psychological problem, I guess, or problem that needed to be solved traditionally it was called the secretary problem, but let's call it the admin problem. Or imagine that you needed to hire an administrative assistant for something, okay, an executive assistant. And you had a stack of 100 resumes that you could go through, okay? Put out this job posting and get 100 resumes in. And you're like, okay, well, I need to hire someone. And let's just say, for the sake of this algorithm, I'll put some bounds on it, that once you interview someone, so you're going to go down through these 100 people. And once you interview someone, you'll either hire them or you pass, right? If you pass, you go and interview the next person. You interview number 2, number 3, okay? And let's just assume that if you give them an offer, they'll accept it. So the question here is then, how many people do you interview before you hire someone? Because if you hire the 5th person, well, what if the other 95 people were better and you never knew, right? But if you get to number 97 or 98, and there's only 2 people left, well, what if they both suck and now you've missed your best candidate? And you can't go back and hire someone you've already passed on, okay? So that was this famous problem called the secretary problem. So the optimal stopping algorithm showed that the algorithmically best or most optimal answer to this question, how many people do I interview before I hire someone, it's called the 37% rule. And this rule is basically that what you're going to do is interview the first 37% of candidates. So if we have 100 candidates, you'll interview the first 37 people. And in those first 37 interviews, you're just going to interview them all, and you will not hire any of them no matter what. You're not going to hire any, you're going to pass on them all. Because what you're doing is getting a sample size of your population, right? You're understanding what's out there, okay? And after you go through your first 37, you're going to pick your benchmark person of those first 37. You can't go back and hire them because you've already passed. But you're going to say, who was my favorite, my best candidate out of those first 37? And that's your benchmark in your mind. And you set that benchmark, and now you're going to go continue hiring or interviewing. And the first time you interview someone as good or better than that benchmark, you should hire them immediately and stop searching, right? That's this optimal stopping algorithm. And basically the theory behind it is that you've found your sample size, so you know what's out there. And 37% is the mathematically correct answer to how much you should search before you stop and make a decision. Okay? But how can we apply that to actual life? Well, this book applied it to dating, which I thought was really interesting. Now, this is all just theory and an algorithm, but bear with me, right? So let's say that the average person dates between the ages of 18 and 40, okay? What is the 37% of that? Well, if we apply 37% to the ages 18 to 40, it would technically be 26.1 years old. Which the theory then here is by the time you're 26.1 years old, in theory, you have dated 37% of the people that you could possibly or would date in your life, right? So you're going to pick your benchmark from everyone you've dated before. And this is not encouraging you to go back to your ex, right? But you're just thinking in your mind, your benchmark, because realistically, you have probably met or dated someone who would make a good life partner for you, right? Maybe you haven't found the storybook perfect person, but you've probably met someone that you could build a life with. So the theory is, by the time you hit 26.1, you pick that benchmark, and the next time you date someone that you think would make as good of a life partner or better than that person, you should stop searching and marry them immediately, because that's as good as it's going to get, right? And now, of course, it's all a theory, it's all an algorithm, but it's a really interesting way to look at something, right? It's a very scientific and algorithmically focused way to look at a very emotional problem. So how can we apply this to cybersecurity? Well, first, a few other fun examples that the book mentioned. Parking is a really good one. I guess you guys don't probably drive as much in the UK maybe as the US, but like whenever you're driving and you're driving down a street, right? And let's say you're half a mile away from your destination. How far should you keep driving and pass up parking spots until you park somewhere, right? Because what if you get to a point now that you've passed all the good parking spots because you're trying to get as close as you can, and now there's no parking spots available anymore, and you have to turn around and do the whole thing again, right? It's an optimal stopping problem. So is buying and selling houses or looking for apartments, right? If you're selling your house, how many offers do you wait for until you accept an offer, right? Because you could say, well, I could take this offer that's on the table, but what if I get a better one next week? Or if you're hunting for an apartment, right? How many apartments do you go tour before you decide, you know what, this one's good enough and I'm just going to pick it, right? Because you could tour every apartment in the city of Leeds, but do you have that much time? We want to optimize basically the difference between how much time you spend searching and how good of a product you get in the outcome. So applying this to cybersecurity, I think the first one we already kind of talked about is very obvious, is actually with hiring. If you're a hiring manager, I know I am at my job, I have this problem where people talk a lot about a talent shortage in cybersecurity, which I think is true for some of the more senior roles. But if you're posting for a SOC 1 analyst, a junior level pen tester, for me, I hire a lot of junior level computer scientists or data scientists. I mean, I can get hundreds of resumes within a few days pretty easily, right? And so as a hiring manager, I have to decide, how much time am I going to spend looking through all those resumes, knowing that I want the best candidate for the job, but I also can't dedicate, a week straight to just reading through resume after resume after resume and interviewing people. So hiring is a really good example of using the optimal stopping problem. But I think so is evaluating and understanding products in the market. So when I look at cybersecurity, I think there tends to be a lot of startups, right? And when I see the market, it kind of ebbs and flows, in which you'll get a bunch of startups, and then the big companies will start to buy them up, right? And you'll kind of get this dip. And then a few years later, a bunch of startups start to pop up, and then they get acquired, and it kind of like goes in these waves, right? But either way, if I wanted a new identity and access management tool that I wanted to buy tomorrow, I could easily evaluate 20 products if I wanted. I could do 20 POCs. I could get 100 salespeople trying to pitch me on their product, telling me why, which one's good, bad, better, At the end of the day, it's probably not worth it, especially if I'm a CISO, to spend so much time looking at every single product I could possibly buy, right? So what you need to do is use your optimal stopping algorithm to evaluate a few products, understand what's out there in the market, because let's be real, a lot of these products are 95% the same, right? And then they all have 5% of something that they do different. So you evaluate what's out there in the market, pick a benchmark, and go with that one. And it's really about understanding how much time should you spend searching versus actually implementing and choosing something. So that's the optimal stopping problem. The next one is scheduling, and applies a little bit more to just like your day-to-day corporate life. So to talk about scheduling, we're going to talk about something called the context switch, right? So we have to operate, when we're talking about scheduling and context switching, under the assumption that preemption isn't free. Meaning if you're context switching from one thing to another, that's not a free thing to do. There's going to be time you're spending context switching, right? That you're not actually getting anything productive done. So the algorithm here is how computers switch between applications. So let's say I'm on my laptop, I'm going to switch from Google Chrome to Microsoft Word, right? The computer has to do things in the background to switch between those applications. So if you want to shift a computer processor away from Google Chrome to Microsoft Word, you see that happen pretty instantaneously, right? But there's a certain amount of overhead where the computer needs to bookmark where it was in the code on Google Chrome, stop running that code, pull up the code for Microsoft Word, execute it to whatever whatever document or whatever you wanted to pull up for Google Chrome, find its place in that code, and then get back into gear, right? That whole process is called a context switch, okay? And that's all preemption. And what's interesting about that is that during that time that the computer is switching from one application to the next, the entire time it's actually not getting anything valuable done, right? The processing power that it's spending is on, wasted materials. It's using its time to switch something, but not actually run what you want it to run. And this is one of the fundamental trade-offs of scheduling, is that the more you take on, the more you're trying to do simultaneously, the more overhead there's going to be, right? And it actually gets to a certain level when it crashes. So this is the degrees of multi-programming, which I'll try not to get too crazy about this, but basically, a CPU can only work on one program at a time. But they switch so fast that it looks like you're watching a movie while you're getting email notifications and getting text messages and all this stuff. But it can actually only do one thing at a time. And so there's a critical threshold when it's switching between different applications that it crashes, right? And you guys have probably seen this before with a computer, right? You start running too many things at once, the fan starts going so loud that you think your computer's going to take off into outer space and then crashes, okay? That's actually called thrashing. And thrashing is this concept of you've taken on so much that you're spending your entire time context switching and no longer getting anything valuable done. And the best real-life example of this seems really simple, but think of a juggler, right? You're juggling 3 balls, and then they throw a 4th ball in, and a 5th ball, and a 6th ball, and the juggler can handle it until you throw that 7th ball in. They don't just drop one ball when they can no longer handle that many, they drop them all. And that's a concept of thrashing, right? The computer doesn't just shut down one application when it takes so much on, the system's gonna explode, right? It can't do anything else. And so the real life example of this, if you've ever had to stop what you were doing to write down all the things that you needed to do, you've thrashed, right? You are now just spending your time context switching and figuring out what you need to do and not actually getting anything valuable done. And it's this entire concept of responsiveness versus throughput, which basically means, how responsive do I need to be versus how much context switching should I do? And a great example of this is checking emails, okay? So let's talk about checking emails. But before we get into that, actually, let's say, so just to get back into the computer science program a little bit behind this, you can think about a computer running different programs, and there's different slices of the pie of the processor, right? The more things that it's running, the smaller slice of the pie that each thing gets to run. Thrashing, again, is this concept that the entire pie now is spent on switching instead of actually running any of these programs. So, example of this and how we can apply this to, our daily corporate lives in cybersecurity. Let's talk about responding to emails. So if you're like me or an average corporate individual, the first thing you do when you log on for the day is probably look through all the emails that you got last night, And if, again, you're like me, you start at the top of your inbox and you start looking, you kind of go through them and you say, oh, this one's for my CEO, let me read that one first, this one, but you scan your whole inbox to figure out what you got, and then you go back and you start answering the important ones first, okay? But to scan your whole inbox, you have to read every email first, okay? And but it's a quick read. And then you go back and then you do an in-depth read when you actually are ready to respond to something and you respond to it, right? This is a great example of spending time doing no real measurable work because you've now gone through all the emails and then have to reread all the emails because the first time you went through them, you didn't really read them that well, right? Whereas, imagine if you just started at the top and one by one went down and dealt with every email. The reason that's actually a lot more efficient is because now you're not reading every email twice, right? You're picking one email, you're dealing with it, you go to the next, you go to the next. You're not jumping around, you're not context switching, you're not doing multiple things. So the theory behind this with responding to emails is that you should decide how responsive you need to be and be no more responsive than that, right? So let's say you're hardcore in some code or setting up some network or something and you get an email notification and you pop over and you respond to that email real quick and then you come back. You've wasted so much time and so much brain power context switching that it's actually really, really inefficient. Whereas if you decide, my SLA, my personal SLA for responding to emails is going to be 30 minutes, right? So once every 30 minutes, I will go respond to any emails that came in and then I'll go back, right? It's actually a way more efficient way of doing it. And it's getting that trade-off between responsiveness and throughput. The next would be this concept called interrupt coalescing. And again, we can, use emails for this example, but it's the idea that you should try to coalesce or group together any interruptions that are going to happen during your day, right? So instead of going and popping and responding to each individual email, you should group respond to all your emails every hour or every 30 minutes. Another great one, I don't know about you guys, but if you have IM, my IM goes off all freaking day long, everyone pinging me because they have quick questions to ask me, especially if you're a manager or something. A really great way to coalesce all of those interruptions is have 30 set minutes of office hours a day or something like that, right? 30 set minutes that you put together on a calendar and you say, hey, anyone who's got questions or needs something from me, hop on this bridge for these 30 minutes, right? Now, again, I know that's not always super practical in the corporate environment, but it's a way to coalesce those interruptions. And the last one, and this actually gets a bad rep, but is weekly meetings. Oh, I'm running out of time. Okay. Weekly meetings, right? So instead of having someone, ping you every single day, tell you their update, it's actually a lot more efficient to have either a daily or a weekly stand-up where you take 30 minutes and everyone gives you their updates, just like developers do their weekly stand-up meetings. So I'm going to zoom through scheduling because we're a little past here. The last one is the overfitting algorithm. Okay, so overfitting algorithm. So here's an example of overfitting. It's pretty easy, right? So you've got an underfitted line, a good, and then an overfitted line. And what's the algorithm here? Well, it's basically that whenever you're taking a model and you're trying to fit a line like you are here through models of data points, the more and more data points or variables you put into that model, a lot of people think, well, the better fitted it's going to be, right? So this line here might just have one input variable, right? It's like a straight line, y equals mx plus b or whatever slope, okay? This one might have a few. Might be like quadratic or something that has a few input variables. This one on the end here has the most variables. It has the most different variables in that equation to fit the line, but it's actually overfitted. And it's this example that a line with more factors in it, more variables, might be a perfect fit to your current model, but might be terrible at predicting the future or past observations, right? So whereas this one is likely going to, the middle best fitted one is more likely going to better predict future data points, the last one is going to be terrible at it. And the computer science relation to this overfitting model would be the more time that you give someone to come up with a solution to a problem, the inherently more complex they will make that solution, even if there's no need for it to be. It's human nature, right? So if you're given a task that you think you should be able to finish in 30 minutes, and your boss says, yeah, spend the whole day on it, right? And you know you can finish this in 30 minutes. It's pretty simple, but they say spend the whole day on it. You're automatically, by human nature, going to make that solution way more complex, and you're going to way overthink it than it needs to be, because you've been given more time to do it. And it's this concept of, you guys have probably heard of it before, Occam's razor, right? The answer that requires the fewest assumptions is generally the correct one, which just means that, when you hear hoofbeats, you should think horse, not zebra. But in general, with overfitting, the theory here is that I really like to go for, it's called, if you cannot explain something simply to someone, you do not understand it well enough. So think about the way that your networks are set up, right? If you're in charge of running networks for your cybersecurity company, if you cannot simply explain to someone how your networks, your VPNs, your firewalls are set up, one, you don't understand it well enough, and two, it's probably overly complex. And so what I like to talk about in terms of cybersecurity and overfitting is this concept of over-engineering, which I think is really, really prevalent in cybersecurity, right? We like to think that we have these crazy, complex, super highly technical challenges, which sometimes we do, to be fair. But I see a lot of times, especially in large organizations that I work with for consulting, there's just a ton of over-engineering that happens in cybersecurity departments. And it's really a concept of overfitting, right? You've given a lot of resources, you've given people time, and they've made these highly, highly complex networks that really, in reality, have more points of failure. Nobody understands. It's harder to manage. It's harder to maintain. It's harder to replace as something new and better comes out, right? So over-engineering is really prevalent and something to be very careful about. And it's this concept, again, of stopping when something's good enough, right? So I see a ton of times that people want to rip and replace a product. Let's say, they've got a vulnerability management solution and they're using Tenable or something. They're like, well, I want to move to Qualys. And it's like, why? Well, Tenable doesn't do this one little thing that I want. It's like, so are you telling me that it's really worth it to invest the time and the money to take out Tenable or whatever vulnerability management product you're using, buy this new product, implement it, train up new resources to learn this new product for one little thing, right? What you're really doing at that point is you're overfitting, okay? You need to stop when something is good enough a lot of the time. And that's not to say you should never try new products or change to things, because there are things that are better, but it's recognizing that you should stop when something is good enough. And really understanding that perfection a lot of times is the enemy of good. I think the best example I had of this is when I've worked for a couple different companies. My current company is definitely more of, if something's good, it's good enough. A previous company that I worked for were definitely perfectionists. And I tried to really figure out why that was so different in the company cultures. My current company is about 450 people. The previous company I worked for was Apple. So it was like one of the largest companies in the world, right? Okay. So what's the big difference between a 450-person company and a company like Apple? The 450-person company, each individual person is responsible for a lot more things because you don't have everyone doing everything. Now, a company like Apple, you have, they want you to be the one perfect subject matter expert at the one specific thing you do because they have 80 other employees who do all the other different things, right? So you're focused more on one individual specific thing. And it really created this culture of perfection because you have such a narrow, limited scope of what you're doing in a day-to-day job that you try to perfect what you're doing. And sometimes that can be the enemy of good. So that's kind of the concept of overfitting. But to wrap up, I do want to say I can acknowledge that life is not an algorithm, right? Life is, and neither is your job, neither is your daily workday. I understand that if you get an email from your CEO, you're not going to say, well, I can't reply for 30 more minutes because otherwise I'm going to thrash and it's too much context switching. I get it, okay? It's not perfect. Life is not an algorithm. And life is not optimal. It doesn't work like a lot of the examples that I showed, right? If it was, my life would probably look very different. But I think this is a good reminder to try different approaches, look at the pros and cons of things, and more so reflect on yourself and understand that humans are not optimal people. We do not make optimal choices. We act against our own best interests all the time. It's the reason that you say, I want to lose 5 pounds, actually. And this morning, my alarm went off at 7 to go for a run, and I said nope, and I turned it off, and I turned it back on at 8, right? And my goal, I want to run another half marathon in a few months, so why did I not go for a run this morning? Humans act against their own best interest, right? Life comes up, we're not optimal people, okay? But I think we have a natural inclination as humans toward chaos, right? We invite bad things into our life. We have a natural inclination towards chaos, and we can never expect to make good decisions if we're just acting off emotion, no logic, things like that. But understanding these algorithms, understanding that we naturally make bad choices inherently can actually help us make good choices, right? So that was I know it's very high level and not as related to cybersecurity, but that's my pitch, is to treat life a little bit more like an algorithm and just see how much more productive it makes you. But yeah, I just threw out my LinkedIn and my email on here, but that's all I had. Thanks for listening.